on patterns of polydimensional movement. Clearance level 10. This presentation was generated by the NEXUS. While the observable universe is often considered to be three-dimensional for the purposes of various hypothetical discussions, this view leaves out an important aspect of our current reality: time. Time is just another dimension, just like height, width, and depth. In fact, just as a comet hurtles through space, we are moving forward in time. Let us imagine that I throw a ball on a carpet. This ball would travel forward in space, moving in a relatively straight line. The ball freely moves to the right at 2 meters per second. That is, over the span of 1 second, the ball travels 2 meters forward in space. If we play the clip in slow motion, we are able to see that the ball slows down. Playing the clip backwards as if we are moving the opposite direction in time, the ball appears to move back towards its origin. This has led to the assumption that movement is dependent on the presence of time, which is not true. But aren't time and space connected? How would the ball move if it has no time to do so? Movement through space and movement through time are not necessarily correlated. We can prove this if we know that time is simply another dimension. Let us look at a two-dimensional plane, which has height and width. An object traveling across this grid to the right does not need to move up and down. The movement through the x dimension, left to right, is completely independent from any movement in the y dimension, up and down, or the lack thereof. The same holds true for any movement through time. Because time and space are separate dimensions, we do not necessarily need to move through both at the same rate. It is entirely possible for us to move through time, but not space. This is how static objects are able to exist. Doesn't this mean that our movement through space is measured in relative units? Correct. Take, for example, the measurement meters per second. If we move at 2 meters per second, this is a relative measurement. What we actually intend to convey is that we moved 2 meters through space, 1 second through time, and that these two actions are correlated. How will we measure our movement through space if not by time? To successfully measure how we move through space and time simultaneously, we will need to create a new unit of measurement. This unit will be used to count how far we move through any given dimension relative to a fixed scale. This means that all units of measurement, such as meters for space and seconds for time, are actually rates. This is because we are comparing them to a universal common scale of units. How does this work? How do we write common units? We will use the capital letter Q to denote these units, which we will refer to as common units. Remember, these are absolute in value. So this means that 2 meters per second would be a relative measurement, but the individual absolute measurements would be 2 meters per common unit and 1 second per common unit. Now let us imagine that an object traveled 8 meters in space and 4 seconds in time, giving us a relative velocity of 2 meters per second. Remember this velocity. Let us also imagine that the said object traveled both these values while moving 2 common units. This makes the object's absolute dimensional velocities the following 2 values: 8 meters per 2 common units and 4 seconds per 2 common units. To test that our new method of measurement works, we will divide one of these 2 absolute velocities by the other. 8 meters over 2 common units divided by 4 seconds over 2 common units equals 8 meters over 2 common units times 2 common units over 4 seconds. These common units cancel out, leaving us with a measurement of 2 meters per second. This is our proof that the measurement system works, because we ended up with the relative velocity of 2 meters per second. The speed has not changed from its original value. Why is this important? What is this used for? Previously, we imagined that we traveled 8 meters in space and 4 seconds in time over the course of 2 common units. But this is trivial. As long as the values for the common units are equal, then the same relative velocity will still be achieved. The normal common unit value for all observable matter is 1. The importance of common units is that they allow us to account for how warped space would affect our spatial travel relative to time. Remember that matter, as we know it, is always traveling through time. If we change the amount of meters or seconds traveled in any one dimension, we are simply altering our relative velocity, but we would still be moving at absolute dimensional velocities with a denominator of 1. But what if we could alter the denominator of our absolute velocity in space? Speaking more clearly, what if we were able to distort or warp space, but not time? Imagine the previous scenario, but with the absolute speeds of 8 meters per common unit and 4 seconds per common unit. The only thing we changed was making both dimensions have a scale of 1 instead of 2. This is done in order to more accurately simulate our universe. 8 meters over 1 common unit divided by 4 seconds over 1 common unit will still give us a relative velocity of 2 meters per second because 8 divided by 4 is 2. Suppose that we were, using an exotic material such as Arena's particles, able to apply a warp factor of 2 to the scale of space, but still keep the scale of time the same. This will alter our calculations. The denominator of the absolute spatial velocity will become 2, but the denominator of the absolute temporal velocity will keep its value of 1, giving us 8 meters over 2 common units divided by 4 seconds over 1 common unit. This is the same thing as taking 8 meters over 2 common units and multiplying it by 1 common unit over 4 seconds. This simplifies to a relative velocity of 1 meter over 1 second. So when we apply a warp factor of 2 to space, then it will reduce our relative speed to 1 meter per second, as opposed to the normal 2 meters per second in normal space. The cause of this drop in relative speed is because the spatial dimension has become twice as dense. Warp factor values over 1 will slow down an object because space gets denser, and warp factor values between 0 and 1 will make the spatial dimension less dense, allowing for travel at faster relative velocities because we change the absolute velocity for space but not time. Why can't we warp time instead of space? This could theoretically be done, using hypothetical Chronos particles which would alter the density of time and therefore the value of our absolute temporal velocity. If we moved at a slower value of this velocity, then we would be moving slower through time than our surroundings, which would essentially send us backwards in time. If we moved at a faster absolute temporal speed, then we would move forward in time faster than our immediate surroundings, which would allow travel to the future. Thank you for watching our presentation. You will now be dismissed.